the general concept of a hypothesis test, let's talk about the actual process for a single proportion. So if you remember back from our confidence intervals unit, we had this question, if we want to test a new drug, should we give it to 1,000 people, or should we have 500 people get the drug and 500 people don't? And they asked a bunch of people this question, and 99 people said that all 1,000 people should get the drug, and 571 said that 500 get the drug, 500 don't. Survey to determine how knowledgeable the population is about basic research design. So, we are going to do a hypothesis test on this data. We want to test whether the proportion of people who would correctly answer this question is significantly different from 0.5. And we're going to use 0.5. That's kind of our people are just as likely to answer it correctly as not, right? If people guessed randomly at this question, we would expect about half of them to get it right. So our null hypothesis for a proportion a lot of times is going to be, what proportion would we expect if people guessed randomly? So our first step for a hypothesis test is to state the parameter, statistic, hypotheses, and significance level. So our parameter is the proportion of, I think this was all Americans, or possibly all American adults, but let's go with all Americans, who would correctly answer the question. Our statistic, our p-hat, was 571 out of 670, which is, I think, 0.85. It was 0.85. Our hypotheses, our null hypothesis is going to be, we said that p is equal to 0.5, which is what we would get if people guessed randomly. And our alternative hypothesis is going to be that p is greater than 0.5. This particular question doesn't indicate whether this would be a one-tailed test or a two-tailed test, but in this case it would make sense to determine if this it would make sense for this to be a one-tailed test. We're interested in seeing if people are more likely to get the question right, if they know the answer, if they are more likely than random guessing. And our alpha level is 0.05. Next step is to name the test and check the conditions. So this is a one sample Z test for P. Just like with our confidence intervals, with our confidence interval, it was a one sample Z interval. Now it's a one sample Z test because it's a hypothesis test and not a confidence interval. Check the conditions. Random. Is it a random sample? We'll say yes. 10%. 670 adults is less than 10% of all Americans. And the large counts, NP0 is is at least 10. And n1 minus p0 is at least 10. So important thing here is that we're using p0 instead of p hat. In our confidence intervals, when we did the large counts condition, we did p hat because that was the only p that we had. For a hypothesis test, we are assuming that the null value is true, so we use that null value for checking our large counts. So n was 670, our p0 was 0.5, that's 385, which is at least 10, and n times 1 minus 0.5, n being 670 again, is also 385, which is 335, not 385. 335, which is also at least 10. So that meets the large counts condition. Independence and the large counts, random 10% large counts. We need to do the general formula, which is the test statistic equals the statistic minus the null value over the standard error. Our specific formula for a proportion, our test statistic is z. If it's for a mean, our test statistic is t instead, but for a proportion, it's z, is the statistic, which was, what did we get, 0.85, minus the null value of 0.5, is our p hat minus p0 over square root of p0, 1 minus p0 over n. And so in this, we're using p0 again instead of p hat to calculate the standard error. For our confidence interval, we used p hat in calculating the standard error. Here, because we're operating under the assumption that the null hypothesis is true, we're going to use p0 instead of p hat for calculating that standard error. So now we plug the numbers in. That's going to be 0.85 minus 0.5 over the square root of 0.5 times 1 minus 0.5 over 670. And that's going to be our z-score, which is root of which ends up being 18.12. So that would be your test statistic, which is one of the things you need to include. Make sure that you have. You also want to sketch the curve. That is something that you always need to make sure that you do in order to get full credit on the AP test. And so, right, our null value is 0.5. We are finding the probability of getting a proportion of 0.85 or greater. So that's going to, there's our picture, and then our p-value This is, we said, was a one-tailed test, so our picture is just the one tail. And our p-value is going to be the probability that the z-score is greater than or equal to 18.12 in a standard normal distribution. All right, this is a normal distribution with a mean of 0.5 and a standard error, a standard deviation of whatever the square root of 0.5 times 0.5 over 670 is. So we find our p-value, and so in order to find that p-value, we're going to use the normal CDF function with a lower bound of 18.12, an upper bound of 1e99, a mean of 0, and a standard deviation of 1. And so because we standardized this, when we divide by the standard error down here, we standardize the test statistic. And so because we did that, we're going to always have the mean be 0 and the standard deviation be 1. And so you plug that into your calculator, and I come up with 1.7 times 10 to the negative 73rd. So that's certainly a number. And then our last step is to conclude. So we have two parts to our conclusion. The first is to interpret the p-value. So our p-value means that assuming the null is true, which you should specify what the null was. The null was that p is 0.5. There is approximately, what was my number? 1.7 times 10 to the negative 73rd. 1.7 times 10 to the negative 73rd probability that we would get a p hat of 0.85 or greater purely by chance. So that's the interpretation of the p-value. And that's the first thing that you need to have. Alright, and so this part is interpreting the p-value. And then the second part is that we make our decision and have the conclusion in context. So, because 1.7 times 10 to the negative 73rd is much less than our alpha level of 0.5, we reject the null hypothesis. And we do have evidence that the true proportion of all Americans who would correctly answer this question is greater than 0.5. Right? Because our p-value is less than our alpha, we reject the null, and we do have evidence that context, the true proportion of all Americans who would correctly answer this question, is greater than 0.5. So this is your decision plus the conclusion in context. Context is key. Context is always important. And that's it. That's a hypothesis test. Tune in next time for a hypothesis test with 2 proportions.